This is the first PowerPoint in our new chapter about gases, and this first initial PowerPoint will simply be an overview of what properties affect gases. So this is just kind of interest. I have a couple slides I threw in here that just because they're interesting. Why are gases so important? Probably the single most important thing I can think of is our atmosphere clearly is all gas. And the atmosphere, of course, supports life in addition to determining weather patterns and many other things. So it's very important to understand their behavior. Some of these properties you're probably familiar with as far back as middle school. But gases are clearly very unique, several properties that only gases have, not liquids and solids. A gas, of course, will expand however far it's allowed to if it's not in a container. Gases are the only state of matter that are significantly compressible. And gases form solutions, homogeneous mixtures with any other gas. And you'll learn why that is later on. It has to do with gases not having intermolecular attractions to one another. But they're not particular about who their friends are, right? They'll associate with anybody. This is an important facet that you may not have encountered before at the bottom here, and we'll go into more detail here too. But it turns out that if you have an equal volume, it doesn't matter which gas, what the identity of the gas is inside that volume, but that if the volume is the same, the number of particles of a particular gas will be the same, regardless of the type of gas. Now, that's clearly not true with liquids and solids, right? So imagine a cup full of water, and then if you replace that with a cup full of gasoline or any other liquid you can think of, and then count molecules of what's inside that glass, there's going to be vastly different number of molecules. So that is kind of fascinating. That's Avogadro's law, which we'll talk about. The first thing I want you to understand is one of the first proposals to describe the behavior of gases was put forth by Maxwell and Boltzmann, and it's called the kinetic molecular theory. And just a few tenets of it that you should be familiar with, that the particles of a gas are in constant random motion. Now that's true for all states of matter, but if you think about it, solids and liquids, the particles are so close to one another, there's not a lot of free translational motion they can do, whereas gases are quite a distance, the particles are quite a distance away from each other, and so their motion is they have much more motion until they bump into something. The second is that the actual size of a gas particle is extremely small, okay, compared to the size or to the distance between two gas particles. So the importance of this is that you'll see in some of our calculations with gases, we will actually neglect the volume contribution of the gas particles themselves because by far and away, the volume of space in between particles is much magnitudes of order larger than the volume of the particles themselves. So that simplifies our calculations. Gas pressure itself, and I don't know why I find this fascinating, it's actually caused by collisions of the gas particles with the container walls, whatever's holding it in. And so anything that increases the collisions or the frequency of the collisions is going to increase pressure. And finally, the kinetic energy is directly proportional to the temperature in Kelvin. So now it's really important, you'll see in all our gas laws that anytime temperature is a factor in a formula, the temperature must be in Kelvin. Okay, so kind of tuck that in the back of your head. Alrighty, this is another just kind of slide of interest here as far as gas pressure. So again, gas pressure is caused by collisions of the gas particles with the container they're in. And again, so anything that causes more frequent collisions increases the pressure. So I would ask you now, what variables can you think of that would cause more frequent collisions. You probably can come up with a few, can't you? So the actual number of gas particles, clearly if you put more gas particles in there and they're running around, there are going to be more collisions. Just like if you shove a bunch more people in a small room and tell them to run, right? So the volume of the container, obviously the smaller the volume of container, the more collisions there are going to be. And the average speed of the gas particles. So obviously if you make them move faster, they're going to be more frequent collisions. How do we do that? The most common way is to increase the temperature. Atmospheric pressure is literally due to gas particles in our atmosphere that are colliding with us and everything else around them. We don't feel the effect of that. We're actually getting beat up. Okay, we're getting the crap beat out of us, but we don't feel it. We have acclimated, we've evolved to adjust to this particular atmospheric pressure, so it doesn't phase us. But I'm sure you've heard that when you're at higher elevations, there's less pressure, right? Why is that? Because there are fewer particles at a higher altitude. There are literally fewer gas particles. And I think as you know that as you go to outer space, there are fewer and fewer and fewer. It's the effect of gravity pulling things toward it. And so because there are fewer particles at high altitudes, the collisions are less frequent, and therefore the pressure we experience and anything around at high altitude experience is lower. And this is another interest slide. I think gases are fascinating. Atmospheric pressure. So a good amount of our weather is due to pressure of the gases in the atmosphere. So I'm sure you've heard about high pressure fronts, low pressure fronts. High pressure fronts are just the fronts that have a lot of gas particles in a small amount of space, right? As opposed to lower pressure, which has fewer. Well, as you can imagine, anytime a high pressure comes close to a low pressure, think of the low pressure as kind of a vacuum. I mean, there's still particles in there, but there are fewer. So when you put them together relative to the high pressure, it's got a vacuum. And so the high pressure is going to be sucked into this low pressure area. And that's the way of our universe. Entropy is always increasing. Forms of energy are always moving from a more concentrated form to a lower concentrated of energy form. But anyway, this movement between high and low pressure is known as wind, right? So, all right. So now back to back to Earth. The next PowerPoint, and actually a lot of them are gonna be the gas laws. How does the pressure of a gas change when we change its volume or its temperature? And so we're going to start getting into that now. A barometer is a device we developed a long, long time ago to measure atmospheric pressure. It's pretty simple how it works. Mercury is used as the material that is sensitive to pressure changes. So in a barometer, the atmospheric pressure is allowed to interact directly with the surface of Mercury. And so again, think of the pressure. These gas molecules are colliding against the surface of Mercury. That is going to cause the mercury to rise up in this tube. And then that's where our units came from. You've seen the units of pressure, millimeters of mercury? They literally came from a barometer. So now, of course, this tube has demarcations of, started out in millimeters, right? And then the height that the mercury went up was an indication of atmospheric pressure, right? So the stronger or the higher the atmospheric pressure, the higher the mercury went up in the tube. There are several units of measure for pressure. The ones that we're going to be working with primarily, atmosphere. 1 atmosphere is sea level atmospheric pressure, okay, just defined. And we will also be working with millimeters of mercury and torr. Notice for a moment that millimeters of mercury and torr are identically sized units. So if I say I have 50 torrs, that is entirely equivalent to saying I have 50 millimeters of mercury. All right, please also notice the conversion between millimeters of mercury and or torr and atmosphere. So there are 760 millimeters of mercury or torr in 1 atmosphere. And so you will have to frequently convert from one to the other. Okay, manometer may be an instrument that you haven't talked about or seen before. So whereas a barometer is designed to measure just atmospheric pressure, a manometer is designed to measure the pressure of some gas for which you don't know the pressure, right? So manometer has a container which contains a gas, and then a tube leading to the atmosphere. And this tube is open to the atmosphere. Inside this tube, again, is our favorite material that's sensitive to pressure changes, and that's mercury. And so I want you to think, instead of a tug of war, I want you to think of a pushing contest between the pressure exerted by the atmosphere and the pressure exerted by the gas in this container. So any gas is going to exert pressure. In other words, the particles are going to collide in all directions, but this pressure is going to cause the surface of the mercury in here, it's going to push down on it, okay? So that's the gas in this container is going to be causing the mercury to go up in this direction. I need to erase, don't I? Okay, here. Okay, and on the other hand, on the other end of that tube, we have the atmosphere. And the atmosphere, made up of gases, is also going to be colliding with the surface of the mercury on its side, and it's going to be wanting to push the mercury in the opposite direction from the gas in the container. So who wins? They're both pushing. They're pushing against each other. Who's going to push more strongly? In this particular picture, you can see that the gas in this container has a higher pressure. That's not always going to be the case, but in this picture, it is. How do we know? Because the gas in this container has pushed the mercury harder. It's exerted a higher pressure on the mercury than the atmospheric pressure gases have, right? And so in this case, this high pressure gas has won the pushing contest. So how do we measure? How do we use a manometer? And that's something that you should be able to do. All right, here we go. So the difference in the two levels of the mercury, okay, here called height of the difference, right? So this would be atmospheric pressure minus gas in the container pressure, right? So the difference. This is the difference in pressure. And so what you're going to do, we know atmospheric pressure. We don't know the pressure of the gas. That's why we're using the manometer. We know atmospheric pressure, so we'll say if atmospheric pressure is 760 millimeters of mercury, what is this pressure? Well, we know that this pressure is higher, right, because it won the pushing contest. And so we know that we have to add whatever this difference is to the atmospheric pressure. So the pressure of the high pressure gas would be 760 plus H, okay, the difference in the mercury levels. I'll go ahead and work this one out. Normally I would save it for class, but since this lecture is a little bit late, in case anyone needs reinforcement. So in this particular example, the atmospheric pressure has a higher pressure. And if you don't see that, either ask me or someone else to explain it to you. So again, think of both gases, the atmosphere and in this case neon, they're both exerting pressure on the surface of this mercury, and clearly the atmospheric pressure is winning. It's got a stronger pressure it's exerting because the mercury level's down farther. And so in this case, to get the pressure of the gas in the container, the pressure of neon is going to be lower than the pressure of the atmosphere. So in this case, we're going to take pressure of the atmosphere, which is 748, and we're going to subtract this difference in height from it. I'll just call it H. Now, this wasn't very nice to me, but I put a little trick in this one, and that is the units of H, the height of the difference, is in centimeters. So, and chemists like to play a unit game here, so always check your units, make sure they match. We can't subtract them or combine them until they have the same unit. So let's go ahead and convert centimeters to millimeters. There are 10 millimeters in 1 centimeter. And so that 5 centimeters is actually 50 millimeters. So now let's go and finish it. 748 millimeters of mercury is the atmospheric. Neon is lower pressure than that by 50 millimeters. And so the pressure of the neon gas in this container is 698 millimeters of mercury. You are going to hear the expression throughout the gas unit of standard pressure, standard pressure and temperature, STP for short, okay? And what that means is standard pressure is the normal atmospheric pressure we experience here on Earth at sea level, which is 1 atmosphere or 760 torr. We're not going to be working with kilopascal. Standard temperature, I've always thought this was odd because you have to be careful later in chemistry because there's a standard room temperature, which is the average room temperature we live in, 25 degrees Celsius, but standard temperature as far as gases, any gas calculation, is 0 degrees Celsius, of course, which is 273 Kelvin. Okay, last slide in this intro PowerPoint. The properties will be focusing on the key properties to define the behavior of a gas: temperature, pressure, volume, and number of moles. And again, just as a reminder, STP, standard temperature and pressure, 0 degrees Celsius and 1 atmosphere pressure. And that's it for the intro.